So, as as Tony mentioned, my name is Olmstead. I work over at Sony Network Entertainment, and I wrote the WebGL layer for the PS4. So, obviously, thank you all for coming, and really, it's been an amazing response with everything, and definitely excited to be here. So Tony gave sort of the grand overview of what is WebGL. The next speakers are probably going to give a bunch of fun, cool demos. And I am here to blind you with computer science. So I'm definitely not going to give you any fun whiz-bang demos or anything like that. But afterwards, you're going to have a much better understanding on how WebGL actually works under the hood. And the reality is that, yeah, you might be using a framework like 3 or any other of the many frameworks, but there's a good chance that if you're really, really pushing the hardware, eventually you're going to outgrow it. And then you're going to need to come down to my level here. So I wanted to start off with pretty much what I did for the PS4 and some of the choices we made here. So let's talk about the PS4. We released in November, the same day this meetup was announced. And actually, we sold 1 million units in a single day. And sales continued to be pretty good, 4.2 million in 2013. And obviously, the best part is that every time you log in, you are running WebGL code. So, why did we end up using WebGL? Well, to be honest, it was really more or less a pragmatic decision. So here I'm going to talk a little bit about the architecture of the PlayStation Store, which is what our team works on. So we really wanted the same code to run on multiple platforms. And obviously, the most important avenue for this is PlayStation hardware itself. So this is the PS3 and the PS4. But we also wanted to support people working in the browser. And this is just to make devs' lives easier in case they were away from their hardware. And really, that's where the WebGL usage started. So actually, most of our devs use Chrome. And if you went to our booth outside, you could actually see the PlayStation Store running in Chrome. And yeah, that was more or less what we had. So in this case, I want to start by giving more of an overview of what it is we actually have. What does our software stack look like? So in the case of the PS3, the bottom is actually Fire Engine. And Fire Engine is a game engine provided by Sony for all licensees. And actually, it powered Journey. So same set of code there. On top of that, we had an API layer we called TriLithium. So this is actually a JavaScript API for drawing a 2D scene. I was not involved in the naming. So actually, this is all bound to a JavaScript VM. And it allowed our programmers to create this UI layer, which is more or less a homegrown immediate mode GUI made to look DOM-ish. And on top of that, our devs ran and made the PlayStation Store. So let's talk about the PS4. So obviously, we had a large code base. We needed compatibility with the PS3. We also wanted some more web features, and we didn't have time to rewrite the whole thing. So we actually have a working port of WebKit that powers our browser. This is more or less where I normally work on the rendering side there. And to actually do the port, what we needed to do was recreate that TriLithium layer, but in WebGL. So that meant for us, our UI framework didn't have to change, and neither did the store. So we had a problem. We had reached a point where launch was looming in front of us, and basically the performance was not there. And really, the user experience was suffering because of it. So we started investigating the issue, And my assertion was it's JavaScript's fault. So for me, sort of the avenue to go would be to attack that bottom TriLithium layer and fix it, essentially. So I started optimizing this layer. I really wasn't getting the performance gains I actually wanted and what I thought was actually possible. So we're really close to launch. Performance isn't there. So what do? Well, as any seasoned developer knows, you burn everything to the ground. And in its place, create something awesome. So, really I only recommend that as a last resort. And I more or less went down this route because I was already touching a good amount of the code. And I really wanted to open up all the optimizations that really I'm here to talk to you about. So with the intro, let's begin. So what do you need to know? Well, first off, if you're actually trying to figure out what's going on with your WebGL application, you want to profile. So you need to profile and figure out exactly where your app is spending its time. And if rendering turns out to be your problem and you're using WebGL, you really need to understand two things. So that's how does WebGL slot into the browser? And you need to know how WebGL works so you can optimize your interaction with the API. So then you kind of walk further up the stack. You need to start thinking about how you're submitting geometry. And of course, you need to ensure that work is being done completely in the animation loop itself. All right. So first off, let's talk about animation frame. So you basically have 16.6 milliseconds to do all your work. And honestly, it's safer if you finish quite a bit before then. So if you finish in the allotted time, you'll get, of course, the silky smooth 60 FPS, the holy grail of all graphics programming. And if you don't do it, you're going to drop a frame. And if you do it enough, your user experience will definitely suffer. The animations themselves will look jerky, the controls will seem laggy, it's not good. And this was more or less the state we were in beforehand. So the other thing to remember is on top of that, the browser is doing plenty of other things that can further limit your frame time. So the big one, of course, is the waste monster, also known as the garbage collector. And you have to remember, it can trigger at any time and take as much time as it wants. It doesn't care. So you also need to know that other browser events are going to happen outside of the animation frame. And this is something we're going to come and circle back to later on. So when you're profiling, we need to look at what happens during a frame. And we use a profiler. There are actually two types available to the web dev, in Chrome specifically. So you have that sampling profiler. And this will essentially take little snapshots to try and determine where the time is being spent within your app. And that's essentially what you find in the Chrome developer tools. So something that's a bit more advanced is a structural profiler. So in this case, you're actually inserting code into your code to figure out where your time's being spent. And this is something you'll find if you use Chrome tracing, and you'll basically litter your code with console time end. But there's an even better solution, which is the web tracing framework. Now, unfortunately, the web tracing framework came out a little bit after when I would have really liked it. But it's a solution from Google, and obviously one of the programmers is a smartass because WTF. So, you have your structural profiler. What do you do? Where do you begin? So really, you want to kind of place markers at various points of interest in your code. For a graphics application, typically there's an update and then there's a render. So these are the sort of things where you want to place the markers and then sort of continue deep diving further and further. And from there, you'll be able to figure out what exactly is going on. So here's a little slide with what the web tracing framework will give you. If you kind of look here, obviously really hard to tell, but over on this side is the update. Over on this side is the render. So this particular trace, it was from an example game on their homepage. And you can kind of see how this is a lot of information. And if you're familiar with Chrome tracing, you'll see it's presented in a much nicer way. With Chrome tracing, you get everything, which is a bit harder to kind of drill down into. So I definitely recommend playing with it on your own. And it also does some other fun things like the garbage collection. So it will actually tell you where the garbage collection is happening. So let's say we ran our application and we were seeing a good amount of time in the render portion. So what do we do? It's really important to know what's going on under the hood. So in this case, I'm going to talk about Blink. I'm going to talk about Blink because WebKit is way more convoluted than Blink. So in our app, we're going to make a WebGL call. So we're in our JavaScript code. And from there, the call goes into the V8 WebGL rendering context. So basically, any of the browser APIs that end up getting exposed to the application, they tend to be auto-generated. And there's actually an interface definition language that generates all this. So this is the same thing with the WebGL bits. So from there, we're going to end up in the WebGL rendering context. And at this point, we're going to handle any sort of validation and any sort of security checks. So after that, we can take a detour to the context support class. The naming's not there. Actually, Brandon Jones, one of the Chrome GPU developers, was telling me, no, your diagram's wrong. Here's how it is now. So there is some sort of context support class that will essentially do stuff like loading a texture. But really where it's going to end up is the web graphics context. So the thing to remember is that WebGL is not the only thing running in the browser. So there are certain conditions that will cause your web page to be promoted to the GPU. And web devs typically do this with a translation of 0. So any of that, they're kind of hoping it's going to promote it to the graphics card, and hopefully it's faster. Now that web graphics context, what it does is it fills a command buffer, and that command buffer ends up getting picked up by the GPU process. So obviously there's a lot of code, and this is more or less the 1,000-foot view. But this kind of gives you an idea on what happens every time you make a call into WebGL. So what's the takeaway? Well, every time you call into WebGL, there's always going to be some amount of overhead, and you're not going to be able to avoid it. It's there completely by design to ensure security, as well as support other things the browser is actually doing. So what this means is there's a hard limit to the number of calls that can happen in a frame. Now the exact number is really going to vary on the hardware, but because of this, we need to make sure we are making the smallest possible number of calls to WebGL. So how do we know what calls should actually occur? Well, WebGL itself is a state machine. So what that means is that whenever you make a call, when you make a WebGL call, you are very likely to be changing state. There's some calls that won't change state, but the good chunk of them, if you're actually doing any work, are going to modify some form of state. So this could be multiple things. So you can affect the entirety of the rendering context. So you can do something like change the depth test you're using, and that's going to be when you change it, it's there, and that's what's happening. You can also change the state of a WebGL object. A WebGL object is basically anything you would make through a create function. So this includes stuff like textures, your shader programs, and your buffers. So if a call that should change state does not actually change any state after execution, this is known as a redundant call. So in this case, I'm going to give you an example. So on the left, we have just a simple batch of code. It's just going to be interacting with the program, saying some uniforms, and then it's off on its way. On the right, I'm giving kind of a diagram on what's happening in the totality of the rendering context, as well as what's happening with the individual program itself. So if we step through this function, first off, we hit GL use program. So this is going to bind the program to the pipeline. You're now rendering with that particular program. You're going to call and modify the uniform. Now in this case, we are taking the alpha within this shader and we're setting it to 0.5. That's cool because we were at 0 before. Now we go ahead and take that, we modify the texture unit a sampler is referring to, and we're setting it to 0. Well, the thing is, it was already 0, and essentially this call did nothing. And of course, if you're doing this, you are paying the price for it, as it's a redundant call. So how do we stop this? Well, this actually requires some brains in the application. Basically, if you are writing a renderer for WebGL, you basically need to mirror the entire state of WebGL within your application. So whenever a call is made, essentially we need to compare this, the current value to the value we want to set it to. And if it's not equal, we can go ahead and let the call slide through. If it is equal, we want to stop it in its tracks. And like I said, the renderer needs to be designed to handle this for every single instance of WebGL call to be optimal. So in this example, I grabbed some of the code from the TriLithium API. And this is one of those cases where we are limiting the number of calls. And this is just a simple functor. It has a current state. When you try and set the value, it compares it to the current value within the functor. And like I said, if it's different, we go ahead and make the call. If it's the same, we ignore it completely. So really, this was a big win for us. The older version of the API did nothing like this. So it drastically cut down the number of calls. And here are some results for you. So at best, we are making a quarter of the number of calls. That meant that in some cases, 3/4 of the number of calls were worthless. And at worst, we seem to be making about half the number of calls we made. And my completely unscientific study of it seemed to say that it was about 1/3 on average. And really, at this point in time, everything started feeling a lot better. It was a lot less scary that I burned everything down. And people were quite a bit more receptive at this point. So with our optimized renderer in place, we need to go higher. Remember, you can still get yourself in trouble if you aren't submitting your geometry in an optimal way. So here are some general rules you should be following. If you can't see it, don't draw it. Basically, you want to compare the geometry to the camera. If the camera can see it, go ahead and lay it through. If it can't, stop it in its tracks. We also want to submit any opaque geometry front to back. Now, the rationale here is if you have a large geometry and it's fairly close to you, but there's another geometry behind it, if you draw that one first, the depth test for that second geometry is likely a fail. And if you have a fragment shader that's taking up a good amount of time, that can save you some work, and it's definitely optimization you should try for. But also remember, on the converse, the opposite is true for your transparent geometry. You want to render them the opposite way. Otherwise, your blending will not look correct. And of course, what you want to do is also to try to group geometry with the same state. And this is to minimize the amount of calls we're going into WebGL. Of course, the most important rule of optimization, optimize for your case, not the general case. You really need to think about how your scene works, you need to figure out your requirements, and you need to design your algorithm around this. And that's how you will really be able to push the hardware in new and interesting ways. So in this case, what did the PlayStation Store's scene look like? Well, the tree was pretty deep. We had a lot of nodes that were basically used to position other nodes. And the worst case I saw was a tree with 26 levels. It was a ton of nodes, not a lot of actual drawable entities. The other thing to remember in the PlayStation Store was our textures were unique. So we would constantly be requesting product images, text, and that didn't really allow us to do sheeting. Texture sheeting is a technique you would use to limit the number of times you switch a texture. CSS can also do something like this, and definitely the perf guys will tell you to do this. So another thing that was characteristic of our scene was the objects themselves weren't too mobile. So that means that really the only time stuff would start moving is when you had user input. And we also had a requirement that some areas needed to be clipped to some bounding area. So with that in mind, what did we do? So since things weren't moving that much, the visible set was only computed when the tree changed. So the visible set meaning we run through our tree, we figure out what is actually available to draw, and we use that to feed the renderer. The scene was deep, so rather than bubbling up the bounding volumes, which is what you'll see in a lot of engines, where the bounding volume of the object below kind of affects the one up higher, and we bubble up, all the way to the top. So this didn't really help us, and it would have created a hell of a lot more work because, as I said, a lot of the things had to do with positioning. And in our case, whenever we use those bounding volumes as the actual points of clipping. And when the intersected bounding volume was met, what we would do is intersect those and use that smaller bounding volume to affect the geometry further down the tree. So let me give you an example of that. So let's say that in the case of the yellowish nodes, those actually have clipping volumes associated with them. So we kind of work our way down the left, and we compare those two clipping volumes. We do an intersection. They do intersect. So then we use that smaller volume to compare the leaf node. In this case, it passes, so it's added to the visible set. So then we're going to continue down over on this side, and we just compare it with that top one, and we find it's within our view, so it goes through. Now we go further down into the right side, so we're comparing these two and seeing the intersection. So there is actually no intersection, so at that point we can say, all right, we're not even going to bother with the rest of you guys. So that's more or less how the algorithm worked in our case. So the last tip for you is to keep your work within the animation frame. So as I mentioned, the browser has a ton of other things going on. does not think you're that important. So there are things that are going to happen outside your frame. And the big one there would obviously be timeouts. And it also includes getting your images, getting your HTTP requests. And of course, remember, if there's an event or series of events that take up a good amount of your time, you can completely drop a frame, and you will be looking at your frame and say, well, I was ready in 5 milliseconds. I don't know what happened. Well, most likely a timeout of some kind happened. So to kind of combat this, we looked at how resources were actually being created within the store. So anytime a user ended up in a new view, there were a ton of requests going out. So we were requesting information on how things are laid out, images, getting text, all those things. And yeah, so a ton of texture, ton of product art, and we also had our text. So to keep the frame rate steady, we decided to basically pay off the amount of time over a series of frames. So to do this, we created a task manager, because why not have an operating system construct in your WebGL program? So it's not really complicated. It's just a simple FIFO, didn't go priority, wasn't really needed. So in our case, what exactly is a task for us? So when image is received, we actually defer the loading to the animation frame. So we get the response. We say, OK, you are a task. I am going to insert you to the queue, and you are going to run at some time in the future. So we also did text creation that way. Our text creation could probably be a bit better. There's certainly some optimizations we could do there, like a bitmap font or things like that. But due to the amount of time of me going nuclear, didn't really have time for that. So we actually use Canvas. And whenever we request a new batch of text, it actually busts it up into 3 steps. So initially, we compute the layout. From there, we take that and draw it into the canvas. And then another task comes around and actually uploads the canvas to a texture. Those last 2 end up being slotted right next to each other, so didn't really have to worry about anything in there. So to keep our frame rate steady, we needed to limit the amount of time we actually took to run these tasks. So that pretty much ensures the application has enough time for anything else it wants to do, like an update and render and all that. So obviously, it's not a perfect solution because there's essentially no way to stop a task once it's started. When you upload a texture, it's going to take however long it's going to take, and that's it. So if you had the case where you set something for, let's say, 5 milliseconds, and you had your task finish at 4, it's going to kick off another one. And if that one goes another 5 milliseconds, really not much you can do. So really at this point, to do that, we more or less kind of played with the numbers and figure out exactly what felt good in terms of the frame rate versus how quickly the assets were appearing. So if you made it super quick, you're always going to get 60, but things are going to kind of creep in slower. So it's definitely a balancing game there. So obviously our task manager, nothing special. First in, first out. We look at the number of tasks. We compare it to whatever our maximum time span is. We pop a task, we run it, we check it, and we keep going until we either run out of tasks or we run out of time. So like I said, nothing special, but it actually really helped us kind of keep that frame rate. So in conclusion here, if you want to optimize a WebGL application, you need to do the following. You need to ensure your renderer is optimal by preventing redundant calls. you need to optimize how geometry is submitted to your application. And really, to avoid any sort of jank, you need to keep the work on the animation frame. So if you follow these rules, you'll be able to really push your application even further and create even more compelling, awesome experiences with WebGL. So now we are in the shameless self-promotion portion of the talk. So this particular talk is more or less a PS4-themed version of an article I wrote for HTML5 Game Development Insights. It's currently available for pre-order on Apress, and it has a lot of great input from other devs, and the pirate guy helped out, who I'm sure you've seen.
Oh, kill your crew.
Yes, kill your crew. All right, so any questions? We're deferring to the QA panel. But here's obviously my contact info on the right. I'm pretty good with G+. I also go to various other speaking gigs, like speaking at the Dart SF meetup next month, because Dart is awesome. And of course, SNEI is hiring. We have a booth here. We have a PlayStation 4. And obviously, if you're a web dev, one of the things that really sucks about web dev is worrying about older browsers. And we don't really have that since we own the browser. So, you're not really going to have to worry about IE8 or anything like that. So definitely thank you guys for having me.